The topic of my talk is stability analysis of a model with general retrials and constant retrial rate. A few words about the structure of my talk. I'll start from the description of the model. Then I briefly present the stability of the stability condition of dominating model. The analysis here is based on Markov chain properties. Based on heuristic approach and results from renewal theory, we extended the previous condition to a general case of a model under consideration. Finally, we verified assumed condition by simulation. At the end of my talk, I'll present the simulation results for the retrial system with Weibull and Pareto distribution of retrial time. Now I'll briefly describe the model. Constant retrial queuing model with constant retrial rate. We deal with the Poisson input to the rate lambda. Service times are independent and analytically distributed with a generic element distributed as S. Single server if incoming customer found the server busy, join to infinite capacity orbit as usual, and then try to rejoin their server after a random time interval distributed as C. The basic features of such a model is constant retrial rate policy. That means that orbit rate, which could be denoted like this, orbit rate is independent of a number of orbit customers, unlike the retrial system with classical retrial policy. And the other important feature is the general distribution of retrial time. Such models are successfully applied in simulation of, at instance, model of telephone exchange, multi-access protocol, and other protocols. Note that most of stability results are obtained for exponential retrial case. Some notation, Poisson input, generally distributed retrial times. The traffic intensity or load coefficient we denote by rho. N of t denotes the number of orbit customers at instant t. We also consider the sequence dn. It is a sequence of departure instant. And here you can see the discrete analog of orbit size. It is the number of orbit customers just after the nth departure instant, departure from the server, of course. When they concentrate on a particular case, we assume that distribution of retrial time, the distribution of random variable C, has so-called new better than used property. Namely, this means that the tail of distribution is stochastically less or equal than the whole interval. The model under consideration is denoted by sigma. We additionally construct an auxiliary model defined by sigma with a hat. We construct this model as follows. This model has the same number of arrival instants as in original system, the same sequence of service times. This model is also retrial model with constant retrial rate. Retrial times are distributed as C, but with the following modification. At departure instant, which is defined by D with a hat, each departure instant, we replace the residual retrial time, the time before the next retrial, we replace this interval by the whole independent time interval distributed as C. So by NBU property, we had the following relation. So we construct this system with slower retrials. So this interval is stochastically less than the red one. Let's concentrate on the departure instance in both systems. The next departure instant in original system is defined as follows. The previous departure instant, the idle time, and the busy period, which is equal to service time for the next customer in the server. The structure of idle time is the following. If retrial is faster than arrival, the idle time is equal to the residual retrial time. Otherwise, if arrival comes first to the server, the idle interval is stochastically equivalent to tau. The corresponding value for the auxiliary, for the slower system is defined as follows. Based on relation between departure instants, we can assume that original system is less loaded than the auxiliary system. A few words about auxiliary system. Here, and with the head, defines the number of orbit customers after nth departure. And in the auxiliary system, we obtain an irreducible, aperiodic, and time homogeneous Markov chain. Unlike the original model. Moreover, the ergodicity of such Markov chain is equivalent to the stability of auxiliary model. Transitions and statements of for the transition probability for such Markov chain in case the orbit is non-empty depends on the following condition event. Here, primary arrival is faster than primary or outgoing arrival is faster than retrial attempt, and here retrial attempt is faster. Note that in original model where we do not modify the residual retrial time, in original model we have to compare tau with the residual retrial time at departure instant, and we are not able to construct Markov chain, but we can do this in auxiliary model. I won't discuss in details the stability of auxiliary model because this material is not new. We relied on the preliminary results. I just can say that under condition 5, the auxiliary model is stable. Moreover, the auxiliary model is stable, and the stability of auxiliary model implies the stability of original model. So here we obtain the sufficient stability condition for the model under consideration in case of an NBU retrial. And our goal is basing on this condition to obtain a more tight stability condition, not only for NBU retrials, but for the general retrial case. From this point of view, we rely on the renewal theory arguments. Note that for the renewal process built on intervals C, and if C has a finite mean and is non-lattice random variable, the following weak convergence for the residual renewal time takes place. Here, C sub S is so-called stationary excess, a random variable with the following distributions. Note that if C has an NBU property, the following relation holds, and the following inequality is easily proved. Our goal is the following. We assume that in a general model with a general distribution of retrials, the actual residual retrial time associated with the departure instant is close to the stationary excess. Stationary excess, a random variable with the following distribution. So we made this assumption and assume that if C has a finite mean and is not lattice, the condition 7 indicates the stability of the model under consideration. And next, we verify our assumption by simulation. A few words about the simulation plan. For NBU retrials, we have sufficient stability condition, and we consider the following configuration of our system. We are able to choose the load coefficient as follows. So the sufficient condition is violated, but the assumed condition holds. For our distributions, we are not able to rely on a sufficient condition. We just verify this one, the assumed stability condition. And we made tests for Weibull retrials and for Pareto retrials. Let's start from Weibull retrials. We fixed scale parameter equal to 1. The shape parameter is denoted by W. In this case, the border of assumed stability condition is defined as follows. Note that in case W is equal to 1, we obtain exponential case. In case W is greater than 1, we obtain an NBU retrials. We start from the exploring of NBU retrials. W is equal to 2. So we have the following statement for the border of assumed stability condition. They fix the rate of the input rate equal to 1 and calculated the following values. Here, the border of sufficient stability condition is the following, and the border of assumed stability condition is the following. Moreover, we know that the only reason of instability of such a system is the infinite growth of orbit size. We estimated the real stability border, so we shifted the values of rho and estimated the value S as follows. If rho is less than S, we obtain the stable orbit, and if rho is greater or equal than S, we obtain the infinitely growing orbit. So we estimated the value of S, obtained the following result. We obtained that the real stability border is less than the border of assumed condition for this particular case. So here you can see the sufficient condition. Of course, the sufficient condition narrows the real stability border. Here we have the real, and here we have assumed. So for the NBU retrials, we obtained that our assumed condition a little extends the stability border. As you can see, the values for real stability border and for assumed stability border are rather close. A few results. For the black line, the sufficient condition holds. For gray line, the sufficient condition is violated, but real condition holds, the system is stable, and of course our assumed condition holds. The black dotted line, all conditions are violated. Some tests for new versus unused customers. The property new versus unused is the opposite property for new better than used. And this property holds for Weibull retrials if its shape parameter is less than 1. We had chosen W equal to 1/2, made the same calculations as in the previous case, except we have no dominating system in this case. We have no sufficient condition. We have just real estimated condition and assumed condition, and obtain the following values. Again, we obtain that the border for assumed condition is a little greater than the real border. So our condition a little extends the actual stability regions. Some tests here, both conditions are condition holds, here violated. And finally, I'll discuss the results for Pareto retrials. In this case, the assumed stability condition has the following border, and the real border is the following. So the border for assumed condition is smaller than real. And in this case, our assumed condition narrows the actual stability region. But note that these values are rather close. So in Pareto case, our condition is sufficient condition because this value is smaller than the real. We also may test for other parameters of Pareto retrials and obtain that the border of assumed condition is systematically less than real border. So here both conditions is holds and here violated. Summarizing the results, I can say that used heuristic approach and assumptions to obtain the stability condition, and verified our assumption by simulation. As we deal with the system with general distribution of retrial time, unfortunately we had to use just heuristic approach. But we obtained the results for different distribution, Weibull, NVU, and Pareto, and the results had shown that our conditions a condition is close to actual stability region, but must be used with care, because sometimes we narrow our region and sometimes we extend. Of course, better results are for Pareto because we narrow stability region, and you can say that we found sufficient stability condition. Okay, I think that was the most important result from our research. Okay, and thank you for your attention, and I'm ready to answer your questions.
Yeah, thank you for your valuable time, and please address the questions to Ruslana.
Yeah, thank you. I am a collaborator of Alex, and I know your advisor, Evsey Morozov. So my question is, there are two Russians by name Mikhailov and Sybakov. What they did was they were working on what were called as multiple access protocols. And you possibly can model multiple access protocols as retrial queues. They have shown that the throughput cannot be any better than 0.52 or so. So are you aware of that work by Mikhailov and Sybakov?
Sybakov.
I didn't actually catch your question. I said that our system is applicable for simulating a number of multi-access protocols, and we know stability conditions for some particular cases, especially for system with exponential retrials, but we consider a more general case and just made an assumption. I'm afraid that I didn't catch the main goal of your question. Maybe you could comment much more.
Just a related work. Yeah. Okay, that's good enough. Yeah.
Okay, I think if it's possible, we can write to each other, maybe discuss it.
Yes, yes.
If you are interested in it, that's for me. Thank you.
Thank you.
I have a short question, if I may.
Yeah, please, welcome.
It's Rostislav. Ruslana, thank you for your talk. Maybe the question is strange, but you know, I'm used to the fact that in single server system, is it the single server system which you are talking about?
Yeah, yeah.
Okay, so I'm used to the fact that in single server systems, the stability region is at when the load is close to 1. So, and in your graphs, I see that the value, upper value was 0.4. So just curious, why is it not close to 1? Why is it 0.4? So I don't know if I'm clear, but this is curious for me.
The condition then the load coefficient is less than 1 corresponds to the retrial system with the classical retrial policy. So when our orbit grows, the retrial rate, some total retrial rate became bigger, and the orbit became more aggressive. But I was talking about the system with a constant retrial rate, and we have extremely large number of orbits customers. Their retrial rates, they're constant, and it's don't work fast.
Okay, I got it. Thank you.
Okay.
Thank you for asking. Any more questions, please?
There is one more question. This is Udo Krieger calling from Germany. Ms. Nekrasova, you have studied the Pareto, which is an example of a heavy-tailed distribution. By simulation, systematically check other classes like the log Weibull or exponentiated Pareto or others to see whether this closeness very much depends on the structure and properties of the heavy tail distribution and maybe their tail index. That would be interesting to see these relationships and sensitivity.
Yes, thank you. It is a topic of our future research. I hope we just tested a few distributions just to check if we are in the right way. So, and surprised that for Pareto results are rather nice. Otherwise, for Weibull, we just obtain bigger, so we extended real region, and it's not good, but anyway we extended. But for example, now example in NVU, in U better than use case, they are rather close but bigger. So I'm going to check other distributions. Maybe we can find some interesting results.
Thank you.
Mm-hmm.
Thank you. Any
Can I add a couple of words?
please?
First of all, I'm happy to hear from Udo.
Yeah.
Best regards from me. I would like to add a couple of words to Ruslana's comments. I think we can make more tight, more correct this condition if take into account some additional information about state of orbit maybe or server, and maybe make more correct this condition, more tight, because actually now it is not clear what we have. We only see that we how to say, we can guess more correctly initial state of situation, and then go further to obtain more correct condition. But I think we must develop this approach more to take into account some additional information of state of orbit or state of server and so on. Thank you. This is my comment. Of course, heavy tail, it's very important to check, as you suggest. Thank you. It's my comment.
Maybe in future we can predict if we would extend or if we would narrow the stability region. So it will also nice result if we can do it. Thank you.